Hello everyone, my name is Bin from Xidian University. It's glad to be here, and my topic is mobility-aware resource allocation based on matching theory in MEC. My content consists of 4 parts. The first part is introduction. With the rapid development of 5G and the Internet of Things, many new applications have emerged in mobile terminals, which put forward high requirements for delay and bandwidth. Although traditional cloud computing provides a lot of computing resources, due to the centralized architecture of cloud computing, a lot of time is wasted in the process of data transmission. Mobile edge computing has become an effective method to provide users with communication, computing, and storage resources closer to the user. Therefore, users can offload tasks to edge servers to improve the quality of the services. In the mobile edge computing, the users in the network are mobile, and the coverage of edge servers is limited. Due to the conflicts between the mobility of users and limited coverage of edge servers, providing continuous service to users becomes challenging. Therefore, the tasks of users needs to be migrated between different edge servers, and we can say in this figure. The edge server needs to provide services for multiple mobile users. In the real, there are 2 challenges. The first challenge is in the real mobile edge computing. The edge server provides services for multiple users at the same time, and there is a task conflict between users. The second challenge is the edge server provides services for users during the mobility of the user, and the service migration is required. Therefore, we proposed a mobility-aware resource allocation algorithm based on matching theory in MEC. And the second part is system model. In this paper, we consider a mobile edge computing system that includes K small base stations with co-located edge servers and end users, and we also consider a time slot system to describe the mobility of the users. And PIKT denotes the probability that UI moves to the coverage of edge server K at time slot T. And the mobility profile of UI, which can be estimated based on the historical moment traces of the user. Here is the transmission model. The transmission rate between user and small base station is given by the following formula. And the Di is the data size of the task of user. Thus, the transmission delay from UI to small base station is given by the following formula. Here is a computation model. Since the task of user may have been potentially calculated in the previous time slot, thus the requirement of computation resources by user UI in time slot T is given by the formula, and the DCI is the total required computation resources of user's task and DCIT is the required computation resources in time slot T. And we consider the users in the mobile edge computing is equal, so the computation resource of the edge servers is equal to the users who choose the edge server. And the computation delay in time slot T is given by the following formula. If the UI chooses edge server ESK to calculate in the time slot T, and the MEC is 1. And here is a migration model. The migration delay between edge server ESP and edge server ESK in time slot T is given by the formula. And the edge server ESP is the edge server the user choose in the previous time slot T-1, and the edge server ESK is the edge server the user choose in the time slot T. And the lambda is a positive coefficient, and the HESP ESK denotes the hop count between the edge servers, and will also denote a binary alpha to represent the migration between edge servers. Because the service of user made during multiple time slots, so the total computation delay and the total migration delay is the sum of the multiple time slots. And the service delay is consists of the transmission delay, computation delay, and the migration delay. So the total service delay is the sum of the transmission delay and the total computation delay and total migration delay. And our goal is to minimize the average service delay of the users. And there are the constraints, service delay constraints, and server constraints, computation constraints, and migration constraints. And the third part is resource allocation algorithm. As we mentioned earlier, the service of user may last for multiple time slots. Therefore, we consider the resource allocation algorithm in each time slot. That is, the user chooses the best resource in each time slot. Thus, the final resource allocation algorithm for users is also a suboptimal solution. This resource allocation problem can be seen as a matching problem between users and edge servers. In our model, the edge servers provide computing resources for users to select, and the matching is between the set of users and the set of edge servers. First of all, we need to do the initialization. Since the matching is between the users and edge servers, each user gives a preference list over the acceptable edge servers, and each edge server gives a preference list over the users that it can provide services. Since our goal is to minimize the service delay of user, the preference list of each user is determined by the service delay of edge servers available, while the preference list of each edge server is determined by the computation delay of user. And step 1 is to establish the user preference list. As we mentioned earlier, there are at most 2 edge servers for any user to select. One is the edge server which the user selected in the previous time slot T-1, and the other is the edge server in time slot T which is closest to the user. If the previous edge server is different from the closest edge server, the user can select one of them. If the user selects the previous edge server, it means the edge server continues to serve user. If the user selects the closest edge server, it means the service needs to be migrated between the edge servers. Furthermore, if the previous edge server is also the closest edge server in the current time slot T, the user has only one edge server to select it. For any edge server, the user can provide services consist of two kinds of users. One is a user who selected a server in the previous time slot, and the other is the closest edge server who did not select a server in the previous time slot. Define the number of the above two kinds of users as NE and NR respectively. Therefore, we assume the number of users which can be potentially be served by the edge server is the sum of the NE and NR. And here are our matching algorithm. And the input is a set of edge server, the set of the user, and the performance list of user and the performance list of edge server. And the output is a current time slot matching result. While some user has task to process, and some user has not matched with edge server, from the user's perspective, the user will choose the best edge server in its performance list. And from the perspective of edge server, the edge server's capacity is limited. While the edge server is oversubscribed, it will find the worst users from the users who have selected according to the current performance list. And we also need to update the performance list of the user and the edge server. And then we will get the matching result in the current time slot T. We use the matching algorithm in each time slot, and we will get a set of matching result, and that is the final result, and that is the matching result of the mobility of the user. And the last part is simulation results. First one is the average service delay of user tasks. And we can see in this figure, the service delay of user increases with the increasing of number of the user. This is because the computation resource of the edge server is limited, while the number of users increasing, and the computing resource each user used is decreasing. As our proposed matching algorithm makes the task offload decision and allocates the computing resources of the edge servers reasonably, the performance of matching algorithm is obviously better than the other two algorithms we can see in the figure. And the second is the successful rate of user task. The successful rate of user task decreases with the increasing of number of the user. When user service delay exceeds the delay requirements of task, the task fails. And we can also see in this figure, our proposed matching algorithm also has the best performance among the three algorithms. That's all. Thank you.